Determine the slope and deflection at C by area moment method. Modulus of elasticity 200 gigapascals and moment of inertia 500 times 10 to the 6 mm to the fourth. Moment of inertia of the portion ABC is twice that of portion CDE. So let's solve for reaction at B by taking moment sums about D, clockwise positive. So we have equals By times 10, then plus 15 times 1 minus 20 times minus 40 times 6, then minus 20 times 12. So By is equal to 46.5 kilonewtons. Likewise, summation moment about B, let's select C as our moment center here. You can select any point, but C is one of the moment centers where moment diagram by parts would be simpler and lesser areas, with lesser number of areas. So moment B equals 0, counterclockwise positive. So we have RD times 10 plus 20 times 2, then minus 40 times 4, then minus 15 times 11. So R sub D is equal to 28.5 kilonewtons. Because we select C as our moment center, let's prepare the moment diagram by parts first due to the load. 20 times 6 is 120 over EI, but divided by E times 2I, so it will result to 60 over EI. Then here, 20 times 2, 40 divided by 2, so 20 over EI. Then due to the reaction, By 46.5 times 4 divided by 2, 46.5 times 4 divided by 2, that would be 93 over EI. Then due to the reaction here, 28.5 times 6, there's no need to divide because the moment of inertia is just I. So 171 over EI. Then 15 times 7 is equal to 105 over EI. 15 times 1, so this is 15 over EI, but not important. So first, let's have EI division of D relative to the tangent at B. So that's the moment of areas between B and D, just between B and D with respect to D. So since there are trapezoidal areas, we will divide the trapezoidal areas into two triangles. I'll just make it two triangles. You can also divide it into rectangle and triangle if you want, but so that there will only be one division. So let's divide them into two triangles. So EI, division of point D relative to the tangent at B is equal to, beginning with positive areas, this one. So this is 1/2 or 0.5 of 4 times 93. The moment arm is 4/3 plus 6. This is 4/3, 1/3 of 4 plus 6. So that's it. Then this one, plus 0.5 of 6 times 171. The distance of the centroid from D is 2/3 of 6, so that's 4. So 0.5 of 6 times 171 times 4. Then minus this small triangle here. Minus 0.5 of 4 times 20. 2/3 of 4 is 8/3, then plus 6. So moment arm is 8/3 plus 6. So minus 0.5 of 4 times 20, 8/3 plus 6. Then this bigger triangle, minus 0.5 of 4 times 60, moment arm is 4/3 plus 6. So 0.5 of 4 times 60, quantity 4/3 plus 6. Then for this small triangle here, minus 0.5 of 6 times 15, moment arm is 1/3 of 6, so 2. 0.5 of 6 times 15 times 2. Then for this big triangle, minus 0.5 times 6 times 105. Moment arm is 2/3 of 6, so 4. 0.5 of 6 times 105 times 4. So using your calculator, calculating these values, deviation of D relative to the tangent at B is equal to 2518 over 3 EI. So positive, so meaning point D is above the reference tangent line at B. So theta B is negative 2518 over 3 EI or negative 2518 over 30 EI. In decimal form, theta B is negative 83.933 over EI. Theta B is negative because it is sloping down to the right as shown in the figure. So that's the elastic curve anticipated. This is the tangent at B. So this is deviation of D relative to the tangent at B, which is positive. D is above, but the slope at B is negative because it is sloping down to the right, or it is below the positive x-axis. So that's why it's negative. Then for the tangent at C on the elastic curve, EI theta BC is just the area between B and C. So we just copy this, remove the moment arm, and this area as well as this area. So equals 0.5 times 4 times 93 minus 0.5 times 4 times 20 minus 0.5 times 4 times 60. So theta BC is equal to positive 26 over EI. So it is positive and its magnitude is less than theta B. So it is sloping downward. So from tangent at B to tangent at C, counterclockwise because that's positive. So this is the tangent at C. So this is theta BC. Let's draw horizontal line. Then this is theta BC from tangent at B to tangent at C, which is counterclockwise, and it is positive 26 over EI. From the tangent at B to the horizontal line, that's theta B. Therefore, from the horizontal line to tangent at C, that's theta C. So it is below the positive x-axis, so theta C is negative. From the figure, theta C is negative of absolute value of theta B minus absolute value of theta BC. So just base it on the figure and make sure that the figure is correct. So theta C is the negative of quantity absolute value of theta B, which is negative 83.933 over EI minus absolute value of theta BC, which is 26 over EI. So theta C is equal to negative 57.933 over EI. Now EI is 200 times 500, so that's 100,000 kilonewton meter square. So divide this by 100,000, theta C is negative 57.933 over 100,000. So theta C is equal to negative 5.793 times 10 to the negative 3 radians, or you may not put the units. So which is the same as in example 100G for theta C, and that was solved by double integration method. Then we compute this deviation of C relative to the tangent at B. So in this figure here, C is above, so we anticipate to be positive. If not, then C should be below the reference tangent. So this is anticipated to be positive. Then the division of C relative to B, moment of area between B and C with respect to C. Then this distance from reference tangent to point C on the beam is, the distance is 4 and the angle is theta B, so 4 times theta B. Then from the horizontal axis on the beam to the elastic curve, that's delta C. And delta C, if this figure is correct, is negative of absolute value for theta B minus absolute value of deviation of C relative to B, if the figure is correct. If not, we will revise that. So EI deviation of C relative to the tangent at B is we copy these areas. We just put moment arms from C. So for the first area, the distance is 1/3 of 4, so 4/3. 0.5 of 4 times 93 times 4/3. Then for this small triangle here, 0.5 of 4 times 20. The moment arm is 2/3 of 4, so 8/3. So minus 0.5 of 4 times 20 times 8/3. For this bigger triangle, minus 0.5 of 4 times 60. Moment arm is 1/3 of 4, so 4/3. Minus 0.5 of 4 times 60 times 4/3. Computing for deviation of C relative to the tangent at B, it is equal to negative 56 over 3 EI. Because this is negative, the figure presented here is wrong. So we will correct it by considering BC in the following manner. So this is BC. This is the tangent at B. And this is the elastic curve. The elastic curve, point C on the elastic curve should be below the reference tangent because the deviation of point C relative to the tangent at B is negative. So meaning to say, point C on the elastic curve is below the reference tangent. So this is the figure. Therefore, this is still 4 times theta B because this is the reference tangent and that angle is theta B. Therefore, the entire vertical distance from point C on the elastic curve to C on the horizontal axis of the beam is the deflection at C. And geometrically, based on the figure, it is negative of absolute value of 4 theta B plus absolute value of deviation of C relative to B. It is now plus based on the figure. So delta C is negative of absolute value of 4 times theta B, where theta B is negative 2518 over 3 over 10 so over 30 EI. Then plus absolute value of deviation of C relative to B, which is negative 56 over 3 EI. So you just add, ignore the sign, then the final sign is negative. So delta C is equal to negative 354.4 over EI. Since EI is 100,000, the shortcut to convert this to mm is you just divide it by 100. So delta C is negative 354.4 over 100, and therefore it is negative 3.544 mm, which is the same answer as in example 100G.